All right. Good afternoon. How are you all? Good? Good. Ready for a great talk? Awesome. Let me announce the speaker next week. It will be Kate Larson, who is director at Rhodium Group, and Kate will talk to us on the road to Paris paved with domestic climate policy. It's a great pleasure to introduce to you our speaker today, Dr. Nicholas Muller, who is an associate professor in the economics department at Middlebury College. Nick is also a research associate at the National Bureau of Economic Research. He's currently appointed as a visiting associate professor of economics at Carnegie Mellon University. Nick teaches microeconomics as well as environmental and natural resource economics, and his research broadly focuses on measuring pollution, air pollution damages and also market-based policy design. He's published widely, including several papers in American Economic Review, papers in Science, and in Nature Climate Change. He has a PhD in Yale in environmental and natural resource economics. Please join me in welcoming our speaker today.
Thanks. So it's a pleasure to be here. Thanks, Varun, for the invitation. And as was mentioned, I'm going to talk about impacts from air pollution. And in particular, I'm going to focus on the social cost from energy production and use here in the US. And within that broad topic, I'm going to focus on consequences of those impacts for alternative measures of output, things like GDP, and growth in those measures of output. So in terms of motivation, just some very general statements, perhaps some obvious statements. Most economic activity relies on or uses energy. Economic activity tends to generate residuals or pollution. And in fact, some of those residuals are priced through markets. So solid waste is an example. When a firm generates garbage, it has to pay for the disposal of that garbage. And the primary reason that it has to pay for the disposal of that garbage is that that garbage has to be put somewhere, usually in a landfill or some sort of solid waste disposal facility. And there are property rights over land. They're well defined. But if residuals are produced that enter other media, like air or water, we tend to think that those types of residuals aren't efficiently priced by markets because, in fact, the media into which they go don't have well-defined property rights. So we can think about things like CO2 or local air pollutants or water pollutants or toxics as among the group of pollutants or residuals that tend not to be efficiently priced by markets. Why does this matter? Well, if residuals are priced, firms or consumers tend to internalize costs associated with disposal. These aspects of cost of production of particular goods are captured by market prices. They're just part of the cost of doing business. If they're not, such costs are hidden, or as economists like to say, they're external to the market. And the implication of that is, number one, the allocation of resources within an economic system may be inefficient. So that is to say, the canonical treatment of the allocation of resources via a price-based allocation mechanism through markets breaks down when prices, in fact, don't capture the full value of either the cost of productions of goods or the satisfaction that consumers obtain through consumption of those goods. Alternatively, measures of output may be inaccurate. That is, if we're in a macro sense not capturing full cost of production, then what we think we're actually producing on net in a given time period may in fact be inappropriately measured. Secondly, when we think about growth in that measure of output, whatever it is, if the degree or the amount of the value of those residuals is changing over time, how we're measuring growth isn't going to be quite right either. And I'm really interested in that first sub-bullet, this one, the allocation of resources. But today I'm going to talk mostly about those latter two, and I'm going to show some empirical results specifically related to those in the U.S. economy over the last 12 years. So I've argued that it's important to price residuals. We can now talk a little bit about broadly who's doing it and how they're doing it. In the air pollution space, I do a lot of work in this area, but there's lots of other folks, and you can see by the dates on those publications and working papers that this is an active area of research today. There are folks at Georgia Tech who are doing great work in this space, folks in the Carolinas and at Duke, University of Minnesota, Carnegie Mellon, lots of areas. I'm excluding some, I'm missing some. Lots of folks are doing work in this space. With water pollution, there's a little bit less work going on in this particular area, but David Kaiser at Iowa State is doing important work. And then you all probably know that I couldn't possibly have enough slides to capture all the folks who are doing damage assessments and external cost estimation in the realm of greenhouse gases. Lots going on there as well. Okay, so why is this useful and important? You probably have some ideas. Policy evaluation, either in an ex ante or ex post framework, is really bolstered or facilitated by estimation of impacts from emissions, particularly thinking about environmental policy evaluation. And in fact, EPA in lots of its RIAs, their regulatory impact assessments, are doing this now as a matter of standard practice, standard policy. They're using tools to estimate the impact of NOx and SO2 and particulate emissions, and they're building that into benefit cost analyses associated with prospective policies or looking backward. And you can probably guess that I was going to say this, given where you know the talk is headed, that estimation of the value of these residuals or pollution damage facilitates the development of alternative measures of output and then tracking growth in that alternative measure of output. So both of these categories of activities that are relevant for policy analyses are facilitated by research that I've listed above that's pursuing this issue of how to price residuals. So I've talked about the introductory sort of motivation for the work. I'm then going to work through both conceptual and empirical modeling. I'll talk about results for a while and then wrap up with just some broad conclusions, maybe some policy implications, and certainly some future directions. So conceptual modeling, there are many relevant conceptual contexts that a discussion about social cost of pollution broadly could fit into, right? From an economist's perspective, one of the first things I did in this area, and the theoretical literature in the 70s did long ago, was to explore what are the conditions that describe or characterize efficient pollution control, right? So how do we think about, from an economist's perspective, maximizing net benefits of pollution control in the context of different pollutants? And how do those programs look compared to the system of command and control standards that we generally have in the US and other developed countries? That's one context we might look at. We might do benefit cost analyses. We might look at cost minimization, that is cost-effective policies to achieve a particular environmental target. I'm going to do something different. I'm going to focus on the integration of external costs, the value of residuals, into existing measures of output, the national income and product accounts, basically GDP. Okay? To do that, I'm going to capitalize on some guidance that's available from the literature. This is the notion of integrating non-market things, non-market entities, into the market accounts is an old idea. It's been around at least since the late 60s. I'm citing here books and book chapters that have particular relevance to the task at hand for me in this research. And in particular, some of you may be aware of the 1999 report that was released by the National Academies of Science. It was called Nature's Numbers. And that committee was chaired by Bill Nordhaus, who is also on my dissertation committee at Yale, and I forget Cocklenberg's first name. And then two subsequent articles that were in an NBR edited volume. The point of me raising this is to say the guidance from that literature is really clear. And it's clear in the sense that it argues that external accounting, non-market accounting, in particular environmental accounting, should try to mimic, in the conceptual framework that it's built on, the market accounts. From the perspective that when one goes to integrate the two, they're both based on the same conceptual underpinnings. And just as an example of what I'm talking about, the market accounts, as you'll see in a moment, are based on values embedded in current market prices. That is to say, we value all loaves of bread at the current price of a loaf of bread. The marginal value is used to value. The price is used to value, not doing something like looking at the integral under a demand curve, wondering what the value of the first unit of bread produced would be. So when we go to do non-market accounting, I'm valuing all emissions at their current marginal value. Now, there are lots of problems with that from a microeconomist point of view, but from the GDP angle, that is to say, why it's done in that context. The motivation for doing it in the non-market context is to create a system of accounts that's as similar in concept as possible to the market accounts. So when you see what I'm going to do, you have some understanding or basis for where these approaches came from. So just a couple equations. Gross domestic product, as many of you might know, is calculated as the product of prices and quantities for the different goods produced in a particular time period within a given economic system, right? Gross external damage, the pollution analog, is calculated in a similar way. The quantities here are emissions. The prices are marginal damages, shadow prices. The way these are calculated is identical in the sense that we're taking our estimates of the current value. Note that prices are really samples of prices from around the economy. They're not truly known, right? We're estimating marginal damages as shadow prices for emissions around the economy. And we're computing the product in a way that's congruent with GDP. So obviously, different market goods and GDP are valued according to different prices. We don't use the price of cars to value bread. It's silly. Similarly, different pollution species are valued according to different damages or shadow prices. That should also make sense. We don't value tons of CO2 according to the estimated damage from SO2. That wouldn't make much sense at all. Perhaps a little bit more subtle is the notion that maybe it's the case that the same quantity of the same pollutant emitted in different places actually has a different value as well that we need to pay attention to. And I'm going to show you some slides in a little bit that indicate a ton of SO2 produced by a power plant in the rural West has an impact, again, the ton, has an impact that's 2 orders of magnitude smaller than the impact, for instance, from the 74th Street station in Manhattan. 2 orders of magnitude, big difference. So part of the early push in this literature was to say, we have to be pretty careful about how we estimate these prices and then attribute those values to emissions from those places because, in fact, the value of those tons is so different. So all that means is I'm adding another subscript or index to the GED equation that says we have to pay attention to source and pollutant within a time period. Okay, some more conceptual issues. How do we build the notion of environmental cost or external cost into some augmented measure of output using GDP? Well, note, as I argued at first, that the GED are in fact unpriced cost of production. Had these emissions been released as solid waste in most circumstances, a firm would have had to pay for disposal. But they don't for emissions that are released into the air for the same property rights argument that I put forth earlier. So these are costs that the firm is not compelled to face. In light of that, the argument in the literature and the one that I'll make here is it's appropriate to deduct the cost from residual emissions, not what's been abated, but residual emissions from their measure of output, be it value added for a sector or GDP for a total economy. That yields environmentally adjusted value added, or EVA. It's just GDP less those unpriced costs. I'm focusing on air pollution and climate today, but you can imagine GED capturing those other pollutant types that I talked about, and I hope it does someday, right? Water pollution, toxins, mercury, other things. 3 remaining issues I think are important to just touch on. How do we think about real versus nominal values in a context like this? Well, we're going to use deflators that I've argued are appropriate to use in an earlier paper. Everything that I'm reporting here when we start getting to quantitative results is in real terms. Okay? Secondly, how do we treat compliance costs for regulated industries? Well, if you don't know, compliance costs are included in GDP. Right? They're costs of doing business. Okay? I'm not capturing general equilibrium effects. That is, as prices for products that are made by regulated industries increase, there are ripple effects through the economy. I'm not equipped to capture that. That's important to note. And then finally, in terms of double counting, are in fact the GED reflected in conventional measures of output? Well, if these external costs from pollution were mainly manifest as impacts on other firms, reduced production, right? The canonical example in Environmental Economics 101 is, I don't know why this is the case, but it's a confectioner, which I think in the olden days was the firm that made sugary sweets and snacks and things like that, and they're bakers, and so they make smoke. And that smoke travels downwind and affects the launderer, which none of this is really relevant today, but this is the canonical example, right? And so if that was the case, if the GED were really firm-to-firm impacts, we wouldn't get the allocation of output right across industries, but we'd get the total number right, because it's all reflected in output. But in fact, for air pollution, most of the GED manifest as premature mortalities or elevated mortality risk, which for markets for air pollution is not captured in GDP. Okay, so I'm arguing that the bulk of these damages, as they manifest for air pollution, aren't already in GDP. So we don't have a big risk here of double counting. Okay, so on to empirical modeling. The way this is done in the work that I do is through the use of integrated assessment models. Integrated assessment models are really a common tool. They're used by federal agencies. They're used by academics and consultants to connect anthropogenic activity through emissions and some physical dispersion model to ultimately environmental consequences. So the integrated is you're integrating different sciences into one modeling structure. They've been around for a long, long time, right? So in the climate space, the earliest climate integrated assessment model was the dynamic integrated climate economy model, which is invented by Nordhaus in something like the early to mid 80s. It's hard to believe. And that work is still ongoing. As you all know, when I referenced the GHG damage estimations literature on the earlier slide, that is when I punted on it and said there were too many to list, they're basically all using integrated assessment. In the air pollution space, this has been an active area of research since the late 70s and early 80s. Note that integrated assessment models, or IAMs, embody a damage function approach. You input emissions, that's the economic activity spitting out residuals, and those emissions are processed through the model to ultimately spit out impacts. Okay? Here's a schematic of what a typical integrated assessment model looks like. The model I use is called the AP2 model. It's been peer-reviewed many times. It's been used by the national academies and other places. The notion that this is a sort of an attempt to mimic the integration of economic human activity and natural processes is, I hope, evident in the schematic here. We begin with, there's a box above emissions or hidden behind emissions, which is production, consumption. That generates emissions, as I argued earlier, and we have to first figure out where those emissions go. Right? This is true in the water pollution space, it's true in climate, it's true in air pollution. And once we figure out where those emissions go and what they turn into along the way, we're not just worried about ambient concentrations. If we were, this would just be an exercise in sort of ambient standard compliance. But we're actually interested in impact, so we have to think who and what is exposed. And after we determine who and what is exposed, we have to determine among that population, surely not everybody's going to fall over dead. So we have to figure what fraction of folks are going to show some impact, or what fraction of ecosystems are going to fail or show some sort of effect of exposure. That's our dose response module. And then finally, because in this case I'm talking about integration of impacts into the national income and product accounts, which are of course expressed in dollars, since I'm talking about that integration, we have to value these impacts, which can be contentious and ugly and make people really uncomfortable. But note, it's not an exercise that says lives are worth X. It's an exercise that says we actually have evidence from people's behavior that they value the reduction in mortality risk in all kinds of contexts. And we use that evidence to convert the changes in mortality risk from air pollution exposure into monetary terms to include in the accounts. Okay, so what I'm going to do is just relatively briefly go through each module and hit the highlights in terms of data sources and data issues and assumptions that are made, so that we're all more or less, if not comfortable, aware of how the model works. Okay? Emissions are provided by EPA. These are the National Emissions Inventory. They are provided in 3-year increments, so I'm not picking those years. That's what's available. There's one earlier NEI, as far as I'm aware, and it's apparently not of great quality. And 2011 is the most recent NEI. Okay, so I'm using the data that we have. These are annual emissions, tons per year, for what ends up to be about 10,000 individual and spatially aggregated sources in the AP2 model. Now, what do I mean here? Spatially aggregated sources is actually how EPA reports emissions from, say, vehicles or locomotives or small businesses, dry cleaners, things like that. So I'm not choosing to make that aggregation for a whole collection of sources and emissions that EPA reports. They report them by county. The model plops them into the right county, allocates them into the right county. Individual sources, I'm looking at about 700 of the largest fossil fuel-fired power plants and manufacturing facilities. Individually, latitude, longitude, coordinate, stack height properties, flue gas exit velocity properties, all those things are treated individually for those 700 sources. For all of the point sources that fall in between the county aggregated sources by EPA and the 700 that I'm tracking individually, they get lumped into the county in which they are reported to exist and treated collectively as one source, which is a necessary, unfortunate but necessary trade-off when doing this sort of national modeling. The county-to-county resolution is still quite good. It's not optimal, but it's still quite good, and yet it's still an aggregation from the detail EPA reports. I'm capturing all emissions of the 5 pollutants here that are reported by EPA to have been released in each data year in the contiguous U.S. And as I said, I know source locations, specifications, and importantly, these are coded by industry, the North American Industry Classification System, or NAICS codes. Okay, so when I do the accounting, I'm able to rigorously connect emission to industry. Air quality modeling links emissions to concentrations. I'm using a very simple approach to air quality modeling based on the Gaussian plume, which is a statistical model. It's been modified to approximate atmospheric chemistry, which is quite important in this context. And in particular, I'm capturing the link between, for instance, emissions of SO2 and formation of ammonium sulfate, which is part of PM2.5. It's PM2.5 that is mostly responsible for premature deaths in the air pollution space. So if you didn't make this connection, SO2 and NOx emissions would be relatively harmless because you're not making that connection explicitly to PM2.5 concentrations. I'm also capturing the connection between NOx and VOC emissions in the formation of tropospheric ozone, ground level ozone, not the ozone layer. We can go into this more in Q&A, but suffice it to say at this point that the predictions from this very simple model are surprisingly positively correlated with the ambient monitoring data that EPA reports. So this is the actual readings of PM2.5 and the readings of ozone throughout the country. These are annual averages, so the model is not able to capture hourly fluctuations. It's not intended to capture, nor would that necessarily matter for national income accounting. There are models that are very good at capturing those fluctuations and pollution spikes and inversions. This is not one of them. Here's a scatter plot just showing the strong correlation between the model predicted ammonium sulfate on the vertical axis and the monitor sulfate on the horizontal axis. These are readings from EPA. Those are predictions from the model, and the correlation is really quite good, 0.86. So ambient concentrations that are produced by the model, here I think for 2005 using baseline emissions, and you can see some patterns that are in effect well known, and so it's important to show that the model capture those. And I'm thinking in particular about elevated PM2.5 concentrations in big cities. It should make sense that the model can capture that because it's well known that emissions are higher in big cities. It's not much transport there. Elevated PM2.5 concentrations in the industrial Midwest, not around big cities, right? And that's coming from a lot of coal-fired power, emitting a lot of SO2, and so the model's capturing that connection between SO2 and ambient PM2.5. And also areas like that in the southeast. Okay? Once we have concentrations, we then need to think about exposures, as I said, and exposures really come down to using census and CDC data, right? So the census reports estimates for non-census years. These are still estimates of populations by 19 age groups by county. So those are in the model, and those are then matched to the mortality rates reported by CDC, which also vary by age. So it's important to recognize age heterogeneity because the mortality impacts of PM2.5 exposure have been found to be proportional to baseline mortality rates. And we obviously know mortality rates are very different for an 85-year-old than they are for a 45-year-old. So that's captured by the model. It's also important to note that this changes from 99 to 2002 to 5 to 8 to 11 as the data changes. Yeah?
Do you value life differently for different age groups?
I have done that and been, let's just say, criticized. So it makes sense from an economist's point of view to value folks with different amounts of productive lifetime differently. And we did that in some early papers. It actually ends up reducing the damage numbers quite a bit because the elderly tend to have a lower value, fewer life years remaining, and disproportionately incur the additional risks from air pollution exposure. So if your population that's incurring most of the risks or have risks that are valued lower, your number goes down. Good question. And then county crop yields, timber yields, these are all sort of secondary effects in terms of contribution to damage. Those data come from USDA, and we also value damages to man-made materials, and that was a data set I put together in graduate school. Dose response, this is the functional link between exposure and impact. I'm not going to say too much here except to say for PM2.5 mortality, which is where most of the damages come from, I'm using very standard choices here. The Kruski and LePoule functions are used by EPA. They're from studies that have been ongoing since, I think, the 80s for a long time. And they track individuals across space and measure their exposure and report the association between exposure and mortality rates. I'm going to kind of hurry up a little looking at the time. There are also non-health dose response functions for the endpoints that don't involve human health, and those come from the literature. Okay, so finally, in terms of valuation, most of what matters here in terms of driving the damage numbers are the valuation exercises applied to human health consequences. And within that, most of the damages come from premature mortalities. And so it's important to say I'm using a VSL, value of a statistical life approach, which is a horrible term that somehow got applied to a reasonable approach. And the reasonable approach is actually isolating the value of very small changes in mortality risks. The VSL takes the number and divides through by the change in mortality risk to estimate the value of a whole statistical life. Awful decision by some environmental economists a long time ago. The value that I'm using, although it's reported in year $2,000, so it's lower, that's for the accounting exercise, is very standard in the literature. I'm not doing anything exotic here. And to Varun's point, I'm not applying that differently to different populations. Just where that number comes from, it's from a meta-analysis, a whole series of studies that EPA has effectively chosen through the Scientific Advisory Board process, I believe. If there were effects that mattered in markets, you would apply market prices current to the year when the impacts occurred for those products. So for instance, the little fraction that comes from adverse impacts on crop yields, the little fraction there is valued at current prices for crops, right? So if you had market evidence, you'd use market prices. When you don't, you use non-market valuation techniques. Okay, so I made a big deal earlier in the talk about the importance of marginal damages, right? Using marginal damages to be congruent with the market accounts that use marginal values or prices. So I'm going to talk a little bit about how I estimate marginal damages, okay? So the first thing I would do, let's say I'm doing this for the year 2008. I would take baseline emissions reported by EPA for all sources and all pollutants and run them through the model to estimate concentrations, exposures, physical effects, and damages. And then what I would do is I would add 1 ton of one pollutant to one source. Rerun the model, holding everything else fixed, and compute the change in concentrations, exposures, physical effects, and damages. And because, I mean, this is artificial, it's a simulation, but it's nice because I can hold everything fixed and just change one thing, the additional ton, to isolate the change in damage from that additional ton emitted by that particular source. then the trick computationally is to repeat that over the 10,000 sources in the model, the 5 pollutants in the 5 data years, and to do that in a relatively efficient manner. All right? So here's an example. This is a now closed power plant, so I can pick on it. It's Ari Berger, which is, you can use the mouse. It's right about here. That is eastern Ohio. And this map is just showing you the change in PM that's coming from a 1-ton change in PM 2.5 emissions. I know it says 100 tons, and I only did that because I'm not very good at GIS, and the 100 tons made the legend more readable, right? But the same effect, the same pattern would show for a 1-ton change. 2 things I want to point out on the map: the importance of prevailing winds and the fact that most of the change in PM happens nearby to the source, okay? So this is the first step in computing marginal damage. Add a ton, compute the change in concentration, and then you compute the change in exposures, physical effects, and monetary damage, and that's what's shown here. And you can see that a lot of the effects happen nearby to the plant, but notice what counties are showing up here. If you know your northeastern geography, which it's okay if you don't, I'll point out. That dark county is Allegheny County, which is Pittsburgh. Lots of people. And it's right downwind from the plant. It was in that dark area of the plume. So the sort of perfect storm, lots of additional pollution, exposed populations on the order of 3 million. But there are also spatially disparate effects from this plant, right? The big East Coast cities, some of the cities in the mid-Atlantic like Washington and Baltimore, and then some in prevailing wind sense upwind, right? What the model then does is sum up these impacts across all counties and store that change in damage as one number, and it moves on to the next source in the inventory and just repeats this over and over and over, storing the spatial sum. So when you look at the results from that exercise, what you see is a case like this. This is SO2, but each county here corresponding to a color, behind that is actually a sum, right? So there's a plume like this behind each of these counties over which impacts are added up, and then they're reported as one number in this map. So these are the spatially specific marginal damage estimates by county of emission, not where the damages happen, but these are the total value of damages from an emission in each place. Okay, so that's important to recognize. The other point of this map is to show that the range of damages is over 2 orders of magnitude, 100 times, right? It's a big deal. It would be a big deal to just assume one value, which the very early literature did because the modeling technology wasn't there to capture this. So we can show a similar map for PM 2.5 emissions, the primary emissions, and you can see this corresponds really closely to population density, which also makes sense given that the biggest impacts are mortalities. And you still have this pattern, right, 2 orders of magnitude between the least harmful and most harmful emission. And the toxicity of these tons are the same in a sort of laboratory sense. It's just all about the population exposure. Okay, so on to results. I'm going to present results in 3 different ways. I'm going to look at levels, GDP, air pollution damage, the GED, and then the adjusted indicator, which is just GDP less GED. I'm going to look at growth rates. I'm going to add updates for 2011, which are from a recent working paper. And then I'm going to focus in, given the nature of the seminar, on energy, fuel extraction, power generation, and broadly the utility sector for results for those areas of the economy. This table is taken from a 2014 paper of mine in Science, and the circle there, or the oval, is highlighting the first set of results in terms of levels, right? These are outside of brackets, just the air pollution damage, and you can see a strong trend in terms of reduced damages in real terms from 1999 to 2008. Damages falling from about 600 billion to about 350 billion. The numbers in brackets are air pollution damage plus damages from CO2 emissions as reported by DOE, valued at the federal government's social cost of carbon of about $38 a ton. Okay? And we can talk about a little bit about how they got to that number. I'm not really the guy to talk about that, but I'm just using an off-the-shelf valuation technique for those emissions. Falling either way, damages. We look at the EVA, which is just GDP less GED, and you can see strongly increasing for two reasons. One, GDP is increasing, and two, the thing that you're subtracting from it, GED, is falling strongly. Okay, so that's going to boost the growth in your EVA measure. I'll show you a picture that makes that clear. And then finally, GED is a fraction of conventional measures of output or GDP, with air pollution beginning at about 6% and falling to 3%. So pollution damage intensity falling by half over this 9-year period. And then with CO2 damages falling from 8% to about 5%. So again, falling, but not quite as much. Yes?
Are we sort of offshoring a lot of that, or are we getting more efficient and lowering the units per equivalent production?
So when you say that, you mean air pollution or carbon? Air pollution is a little bit easier to talk about. A lot of what's going on there is abatement within the utility sector, right? A lot of what's driving these results is air pollution from power plants. Not entirely. I'm sure there is some offshoring, in particular with respect to manufacturing. That's absolutely true. And then it's been documented in terms of carbon that the economy is decarbonizing, right? I can't parse out what fraction of this is due to that effect, but it's certainly going on. Okay, in terms of growth, you can see these are annualized rates of growth over the 3-year increments, right? Strong reductions in GED, whether you're including carbon or not. And then when you get down to measures of growth in the output, you have GDP. This is just data taken from the Bureau of Economic Analysis. I didn't do anything to this data. 2.5% annualized, 2.75% annualized, and then falling as we start entering the Great Recession. Right? It's 2008, so things are getting pretty ugly about this time. Importantly, when you look at the growth rate in the adjusted indicator, so you subtract off the damages from air pollution and climate, your growth rate goes up, which when this came out of the simulations first, I must have spent an embarrassingly long amount of time just double and triple checking that this was right. It was not what I expected. And then when you sit down and you write down the model and you look at the signs of the changes in the two things, it makes perfect sense. And I'll show you the graph that elicits that result in just a second. So I'm going to quickly go through the 2011 results quickly, only because not a lot has changed. Damages have continued to fall. Pollution intensity has continued to fall. Air pollution now about 2%. Lots of additional abatement and coal closures. Coal power plant closures have dropped damages to 2%. And then here the orientation of the growth rate stays the same. About 1/3 of a percentage point faster when you account for air pollution and climate damages. Here's a map showing the ratio of damages by location of emission, state of emission, to state output for 1999. And lo and behold, North Dakota and West Virginia pop out with damages on the order of 20% to 35% of state output. Unbelievably high number, right? I don't have a lot of time, so I'm not going to go through all the other states. But what I am going to say is when you look at the next map, you can let your eyes interpret the map because I've held the colors and the numbers fixed. 2008. Dramatic reductions in pollution intensity. The only state with damages now just above 10% of state output is West Virginia. The vast majority of other states have damages under 5% and many under 2.5% of output. Just, again, dramatic changes. Now, I don't have time, but there were a lot of interesting policy changes in the air pollution space that happened between 1999 and 2008. Not the least of which was the onset of phase 2 of the acid rain program, which lowered caps on SO2 significantly. Okay. I'm going to go really quickly through these. This is just showing the sort of spatial resolution of the model. These are damages by county of emission for coal-fired power plants, all for 2005. For steel mills, for cement manufacturing, I assume these slides are available, right, so anyone can go back and look, and for petroleum refineries. So all of these different industries have different spatial signatures, if you will. The model's capturing emissions from EPA. It's valuing them according to the techniques I showed, and then reporting them here by where they occur, where the emissions occur. Okay, so energy, fuel extraction, and power generation, these are showing just emission quantities over these different source types, and you can see what really matters from this slide and the next is most of the emissions of primary PM2.5, NOx, and SO2 are coming from power generation. So to speak to your point, right, there's a lot of abatement that's going on in that sector, and there are a lot of emissions still remaining from that sector. These are cumulative distribution functions, the graphs, but again, zeroing in on the sort of what matters for interpretation, the circles are characterizing marginal social costs, that is, dollars of impact per unit of output for three extraction industries and one power generation. So for coal mining, this graph is telling you that in 2002, air pollution damage, not water pollution damage, not damage from combustion of coal, but just air pollution damage from mining of coal was not a big deal. 20 cents a ton. Tons now sell for about $45 a ton. I don't know what they were in 2002, but it gives you a sense, order of magnitude sense. Also fairly small air pollution damage from oil and gas extraction. Has nothing to do with combustion of the product, just the extraction process, refining. But it's when we get to power generation that you see social costs that are really a significant share of market prices. So in 2002, damages, social costs were on the order of $65 per megawatt hour, or 6.5 cents per kilowatt hour. At that time, national average power prices were about 8 cents, give or take. 6.5 cents of social cost to 8 cents market price. Just imagine a tax or a fee that reflected those social costs. That's a massive change. Importantly, from this slide, those costs, those social costs at the margin have been falling significantly. It's hard to see, I apologize. 65 to 55, 55, and 45. Right? So falling by almost a third over that, so this is 2011, 9-year period. I'm going to skip this slide. It's just showing the aggregate damage by state from these 4 areas of the U.S. economy. Now, here's the final set of results. I think this should be good in terms of timing. So this is just for the utility sector. The utility sector includes power generation. It also includes things like incineration of solid waste, in some cases, sewage treatment, steam, heat, and air conditioned supply, stuff like that. So you have market value added, basically flat in real terms, around 200 billion, give or take. You have the GED, the air pollution damage, no climate in this case, falling by almost 2/3, 180 billion in 1999, falling to 65 billion in the year 2011. So you subtract one from the other, and you get a difference, EVA, that is growing rapidly, almost a 6-fold increase. Compare that growth rate to the value-added growth rate, which is basically 0, 1 or 2%. Okay? Here's the picture that speaks to it really well. That top line is value-added, the solid line. The red line is damage, GED. I've been saying this whole talk that it's falling. Here's a clear picture showing that it's falling. And the math of this is just subtract the red line from the black line and you get the dashed line. And then, it's pretty obvious that the dashed line is catching up, which means its slope is greater than the black line. And the growth rate is implicit in the slope. So you just look at that picture and you say, oh, that bottom line has to be growing more quickly than the top line. And that tells the story. In an economy or a sector where the external cost is falling while conventional output is growing, you have to have a case in which your augmented indicator, market output less pollution damage, is growing more rapidly. That does not mean, importantly, that does not mean that has always been the case in all of history in the U.S. economy. I hope that's clear. Nor does it mean that's true in other parts of the world today. I'll say more about that at the end, but just recognize this is a case over 12 years in the U.S. economy as a snapshot. This is mapping out the change, not up to 2011, but 1999 through 2008 in the utility sector. Significant reductions in the sort of Rust Belt states, big reductions here in Texas. Only 3 states with increase in damage, and the increases are very, very small. It's additional natural gas in California. It's a big state on the map, so it looks like, you look at it, but it's really a small change in damage over this time period. And then this is the difference in growth rates. Focus on the right-hand column. I presented this actually to a bunch of utility executives about a month ago, and they laughed. I mean, what else are they going to say? But the growth rate here in the EVA for the utility sector annualized from 99 to 2011 is over 15%. The market growth rate's under 1%. That's just telling that story in a different way. If you look at the manufacturing sector, not really as a robustness check, but just as a comparative case, you see the same orientation of the difference, but a much smaller difference. And that's just the function of the fact that the manufacturing sector contains a lot of industries that aren't very air pollution intensive. Right? This can be manufacturing of microchips or dog food, but also steel. Okay, so conclusions, about right. Costs from residuals are often outside of the market accounts. I hope that's intuitive. There are implications of that for measures of output and growth. Just summarizing the results for the U.S. over this time period of 1999 to 2011, the GED ranges from about 8% to 2% of GDP. The GED is falling, and it's falling sharply while output by and large is growing, and that implies that the adjusted indicator must be growing more rapidly than GDP. It's, in growth terms, it's a happy story to include damage, external cost, into this augmented indicator. This is what I just said a moment ago. I've done very little work in this area, but I've started to look back through the 20th century. Emission estimates are pretty sketchy, but there are some. It turns out this was not the case prior to 1970. That is to say, if you did this kind of accounting prior to 1970 and you looked at air pollution, the orientation flipped around. That is to say, the market account was growing more rapidly than the adjusted indicator. That is, GED was rising, not surprisingly given post-war growth. I'm conjecturing here, but what the heck, I think if you did this exercise in China, you would find that a lot of the growth that we've observed would go away, in a sense, if you internalize some of these impacts. And then finally, just in terms of future directions, the model I use has the capacity to run Monte Carlo simulations, so statistical uncertainty is within reach. It's just a question of time. David Kaiser, as I mentioned, is doing a lot of great work on water pollution at Iowa State. It would be great to integrate water and air. And then finally, the next emissions inventory comes out the summer after this one, and that's always a fun time to build that in and generate new results. Thanks.
Do you have any questions?
He's got a mic.
Hi, thank you for your talk. I was wondering, in terms of your study, where do subsidies come in terms of subsidies for fossil fuels, and how those impact your results?
So in the accounts, they show up as government expenditure, just on the market side, right? So they show up as government expenditure. Two, they're going to influence production, and they're therefore going to influence emissions. So on the one hand, one reply is they don't come in directly in the sense that I'm able to isolate the effect of the subsidy, but their implications in terms of productive choices, distortions with respect to what fuels are used to do different things, are evident in the actual accounts, which are then evident in the actual emissions, which then processed through the model are evident in damages. So another interesting question would be to say, what if those subsidies were either changed in some way or replaced with different policies? The result of that, I don't really know what it would be, but you could ask that kind of question in a quantitative way with a model like this and generate an answer in terms of what those subsidies mean for damage and social cost. Likewise for taxes, right? I think the guy down here was first.
Oh, sorry.
Your slide on SO2 damage wasn't up very long, but it looked like one of about the two most impacted counties was San Diego County, and I was wondering if that was due to, right there, was due to the fact that Mexico generates a lot of electricity for the California market, but doesn't have the restrictions on pollution that the U.S. and California especially does.
It could. But notice what this is showing you is if you release an additional ton in San Diego County, I do have the right county here, right? If you do release an additional ton here, what is the damage? It's not saying what are the total damages from SO2 and particulate pollution. Your point's valid, though, in the sense that presumably power production or just economic activity south of the border generally is contributing to baseline air pollution, and therefore when I'm computing damages on top of that, the marginal damage, that's going to be reflected in that computation. So I take your point.
You calculated damages from electricity generation. I think you said $65 a megawatt hour. Have you broken that out by fuel?
Yeah. So the two that I can speak to, there's an article in 2011 where we did a far more resolved exercise in terms of the accounting. The spatial resolution was the same. But we went to, I think there are 850 industries in the economy, something like that. And we did this accounting exercise for every industry. And within power generation, we explored by fuel type. And so what we found, if I remember the numbers correctly, that the damages for coal-fired power were on the order of, so this is a different year. So now we're using a different assumption. I believe they're about 8 cents a kilowatt hour. And natural gas was much, much lower, right? It was in the order of 1 to 2 cents per kilowatt hour. So the differential affects a couple things, as I'm sure you know, emission rates, but it's also true that coal-fired power plants are in different places than the natural gas fleet. And I can't, off the top of my head, characterize how those are different, but they are different. And so a model like this is going to pick up both the emission rate intensity, but then also the locational impacts. Oil was in between the two, but oil is now such a small share of power generation, it almost doesn't matter.
Thank you for your presentation. I hope I can couch this question in a way that it makes sense, but it seems to me that the way we, given the difficulties and the challenges of accurately pricing damage, both by concentration and by the activity of the individual species of pollutant, that this method accounts for the damage against a national figure like gross domestic product. And yet the generators are private industries and entities that, externalize these costs, and so we don't really know the real value. There's no real market value of their product or of energy, for example. And it seems to me politically that that's exactly why we don't have an energy policy in this country, is because then we would have to account for those damages and assign them to the industries, or at least, or perhaps even to the corporations that are contributing them. So is that the next step in this kind of research, is to try to figure out how to accurately assign the real costs to a life cycle process,
Right.
where you can truly come up with a market value for some.
When you say market value, do you mean a market-determined value or a value that a third party like a government introduces into the market?
Well, for
through
example,
a tax or something like that?
Yeah, you characterize the penalty cost, say in energy production, in a cents per kilowatt hour
Right.
fashion. That can be attributed to the generator,
Right.
And that's what I'm thinking of.
Yeah.
Is
So there's a couple things to say here. One, the sort of traditional micro approach is to think about what are called Pigouvian taxes. And an emission tax. Pigou was an early environmental economist who developed the idea. And the idea is these are external costs. The firms don't face them. So some third party has to step in and represent those costs. And that can be done through a tax. It can be done through other policy instruments. So that's a sort of standard approach. I fully recognize that Tax itself is a four-letter word. You know, thinking about the political feasibility of additional taxes now is really challenging. I will mention that there's a strain of the literature in environmental economics that has gained a foothold in policy discussions that argues that there are two reasons why we tax generally. We want to change behavior or we want to raise revenue. And it's really great when you can do both of those. You want both of those things from the same instrument. So we have income taxes, but really we don't want to discourage people from working. We could have environmental taxes, and we want the revenue and we want the change in behavior. So that literature is saying, well, why don't we alleviate the income tax because we don't want the distortion and replace it with a tax where we do want the change in behavior. So that's one answer. Another point is to say that it's hard to imagine, but in the early 90s, the BEA, the Bureau of Economic Analysis within the Commerce Department, was actually pretty far along in moving towards very primitive environmental accounts. And there's a case that I always give to my students in class where the BEA and Congress was seriously considering this, and a representative from West Virginia stood up and said, if you do this, you're going to find that the coal industry is worth nothing. Meaning, if you subtract all of the costs associated with extraction, transport, combustion, water pollution, we're not going to be left with any value added. And wouldn't you know that the later research showed negative value added for coal-fired power when you subtract off all these. So there was a movement to actually do this, at least in an accounting sense, and as you correctly note, the sort of vested interest stepped in and said, you know, no, sorry. And then Senator Byrd at that time stepped in and said, no, these are friends of mine. You know, this stops now. And it did. It stopped in '94. It's a good point, though. Yeah. Oh, sorry.
I have a question too,
Yep.
actually. So regarding environmental accounting, it comes up in several discussions, like it could be even at the climate change summit in Paris, and then there's where utilities have to do avoided costs for their energy efficiency analysis. Emissions are a component of that. So how do you see this? I mean, is this something that you expect to get absorbed? Do you have competitive models? Like, how does it really work in terms of this coming into an actual policy discussion and implementation?
So I've given a version of this talk at CBO, Congressional Budget Office, and there are generally two reactions. One is, you know, the sort, not at the figure that showed the convergence of the two curves, of the difference in growth rates that we observe. And there's great hope in the sense that if you actually internalize these costs at some point and then track the change, firms are actually being rewarded then for abatement in the sense that their costs are falling, right, as emissions fall. So that's one piece. The second piece is, again, speaking to the gentleman's point to your right, things are in such a state politically where dramatic changes to a system like the NIPAs, the National Income and Product Accounts, to include these estimates of social cost or damages from climate change, from GHG emissions, it's just at a point where it doesn't seem likely to happen in an operationalized manner given the current political climate. So that's a fair point.
Thank you again. So I just want to learn a little bit more. So for example, carbon dioxide that's emitted in China or the US or Europe, that's a global situation. But are these criteria pollutants all fairly localized? So our pollution really affects us with those particular pollutants?
I wouldn't say, if by local you mean, say, within the county?
Or even just mostly, is China protected from our pollution by our oceans, for example, and vice versa?
Not completely. So from my interaction with environmental engineers who are running global circulation models, et cetera, and from my understanding of some of the monitor data in the Sierra Nevadas, right, they're picking up sulfur compounds that could only have been released by China, and they know that through the composition of coal that's being burned there. So it's not strictly true, right, that this is a local thing. But one thing you can show pretty clearly is if you look at the change in concentration resulting from an emission from a particular source, the rate of decline over space is incredibly steep, such that at 500 miles, 1,000 miles, you've got a tiny little bit left, but it's not very much at all. So the impact of power plants along the East Coast in Europe may be measurable, but I don't think it's a first-order concern on regulators' radar screen in Europe.
And second quick thing, have you done any quick calculations about the Volkswagen cheating, diesel cheating,
I was
and
just
how much?
talking about this with folks, so I don't want to scoop my paper. It's in review, but between 50 and 100 deaths. I did just scoop my paper, but oh well. And now that doesn't reflect the Cayenne, the Touareg, and the Audis that, yes.
Hi.
Hi.
I was definitely intrigued when I heard about your talk, so I'm glad to be here, and thank you.
Thanks for coming.
I've never really heard of this kind of analysis, so I was glad to be here. My question is, like, for fracking, if you look at the worst case scenario, all the different things, I mean, it can really add up. I mean, you've got 18-wheelers, you've got methane emissions at ground level, then you've got the combustion, and you've got, you know, there was a documentary on these towns in South Texas where you have 18-wheeler traffic jams, and you're like these towns that are taken over by workers and so on. So how deep do you go into your analyses? And then earthquakes in Oklahoma,
Right.
so on. There's a lot of damage there too.
So I can't speak to some of the more important effects, which I was learning about this morning from a faculty member here, which are, include the habit of taking the wastewater and trying to process it through a municipal sewage treatment plant that has no capacity to deal with the compounds in the water. I can't speak to any of that. Air pollution is what I do. But I can speak to the notion of having significant increases in diesel vehicle traffic, in particular idling. We know that ground level emissions of compounds like this, so from diesel you're talking about sulfur and fine particles, the soot that you see come out of a diesel truck, are some of the most harmful that there are because they're emitted at the ground and because those two compounds are particularly apt to form PM and therefore affect mortality rates. I have not done empirical work to calculate what those damages are from increased vehicle traffic or from the compressors and pumps that are running at the actual extraction sites. But I do know that when comparing the damages from different emissions, those are some of the most dangerous. But that's only a slice of the full impact of that activity.
What about measuring fugitive methane emissions?
Greenhouse gases aren't directly measured in this model, but we know fugitive methane emissions could be a huge deal given I think it's 13 or 20 times greater global warming potential than CO2 emissions. So even, I thought someone said something, even small fugitive releases of methane could make a big difference in what we think is the wedge between coal-fired power and gasoline-fired power. Not gasoline, natural gas.
Thank you so much, Nick.
You're welcome. Thank you.